All right, apologies for the delay getting started. So today's lecture, we are starting in Chapter 5, and we have a new homework assignment that consists, actually it's the assignment from Tuesday, but it consists of the first part of it is that last topic we talked about in Chapter 4, where we were looking at the specific heats for ideal gases, solids, and liquids. Today we're moving into flow. So previous to now, we've been talking about closed systems, where there is no mass crossing the boundary. Now we're going to start looking at open systems where we have to consider mass as it crosses the boundary. So there's important considerations that go into that. First is the conservation of mass, but also the energy that comes into and out of the system because there is a fluid flowing into it, because that fluid by nature has some energy associated with it. And there's also energy, like internal energy, but there's also some energy because that fluid is actually moving. So we'll talk about that today. We'll look at a couple of different types of systems that you might encounter in open flow. And then we'll look at the energy equation and how it differs from that of a closed system, because there's an important difference that we'll talk about when we get to it. So first, if we review back to conservation of mass, we talked about this early in the semester, but it's similar to energy. The mass has to be conserved. We can't have an increasing quantity of mass without somehow accounting for it somewhere else. So mass can't just be created. There is a conversion between mass and energy as theorized by Einstein, but the change in mass that comes about due to a conversion from energy is pretty small. So we don't generally have mass being produced as a result of energy, and it takes such a significant amount of energy to do that it wouldn't really ever be feasible or profitable to create mass. In a closed system, the conservation is implicit. Because there's no mass crossing the boundary, we don't ever worry about the mass changing. We may need to know changes that involve going from one phase to another, so we might be concerned with how much of the mass is in a liquid state versus a vapor state, but the total amount of the mass in the system doesn't change. Okay, now as we move into open systems, we have to consider that fact. We have to know whether or not there's a mass accumulation in our system, whether what's coming in is equal to exactly equal to what's coming leaving the system, or if there's some change in the total mass of our system due to what's flowing in and out. So we'll look at all those different scenarios, different types of problems as we go through Chapter 5 and into Chapter 6 that we will deal a lot with mass flow. We've used mass flow rate already in our problems when we were just looking at some simplified versions with velocity of flows in reservoirs. But mass flow is important to know that it's a path function, so it's very much dependent upon how it flows through the cross section and what the difference is between the mass flow vector and the velocity vector. So in general, the equation for that is actually integration across the cross section. So you take into account the density of the fluid, the velocity of the fluid, which has a directional quality to it, and then that cross-sectional area. But because it's not really always practical to do that, it's not practical to account for the mass flow at any direction other than parallel to the velocity vector, we will just always, in this class, simplify it so that the mass flow is just equal to the density times the velocity times the cross-sectional area. So we don't have to worry necessarily how the mass flow is changing across the cross-section. We're going to assume some average value for mass flow. And that's a fairly accurate assumption for the types of systems we're dealing with. If we were dealing with nanoflows, it would be a bigger error to consider that. Similarly with velocity, the velocity is not always uniform across a pipe or an opening. And in many cases, it's actually zero at the walls, and it is some maximum at the center due to frictional forces at the walls and boundary layer flow and things like that. But we can take an average velocity, which is 1 over the cross-sectional area, and then integrating the normal velocity across the cross-sectional area. So we're finding this average velocity Again, we don't often have to do this because in many cases we don't necessarily know the profile of how the velocity is changing across the cross-section. And if we can measure the fluid flow or somehow that average velocity is just given to us, then it's easier in practice to just use some lump average velocity rather than integrating every time. And volumetric flow rate is related to the velocity as well. So the velocity multiplied by the area is equal to that volumetric flow rate. And as we've discussed previously, in fluid mechanics, they use Q for flow rate. So some of you, if you've taken fluid mechanics, will be familiar with that. However, we use Q for heat transfer. So to avoid the confusion and to stay with the standard nomenclature that we use in a lot of other variables is we just put a dot over a capital V. So that indicates that the volume is changing with time. So the unit on volumetric flow rate in the metric system would be meters cubed per second. Okay. Mass flow rate, which is m dot, is kilograms per second. Those are two very different variables. That mass flow rate is related to the volumetric flow rate by the density, but they are not the same thing. Okay, so it's important to remember that. And then as we remember from early in the semester, the specific volume is the reciprocal of the density. So in most cases in our problems, we look up the specific volume in the book so we can relate volumetric flow rate and mass flow rate in that way using that specific value, that specific volume value that we look up. Also in fluid mechanics, many times you just use a constant density of 1,000 kilograms per meters cubed, right? That's usually what you use for water. Well, in our problems, we're going to have water at varying pressures, varying temperatures. We can't always just assume that density because we can go to the tables and look up the specific volume, and it's not going to be the 1,000 kilograms per meter cubed that we would find if we took the reciprocal of it. So don't just automatically make that assumption of the density. You need to look in the table and look up the actual value. If it's a compressed liquid water and it's at ambient atmospheric conditions and you're not really told any other information about it, to look up a property value in the table, then it's okay to use that value. So conservation of mass, similar to conservation of energy, states the total mass entering minus the total mass leaving has to be equal to the net change in mass within the control volume. And you notice in this case that it's entering during a specific time period, because generally in steady flow problems we look at them over some certain time interval or a time period. So we may say, okay, at t equals 0 we start filling up this bathtub, at t equals 20 seconds we pull the plug. You know, how do those mass flow rates balance in and out? Or maybe we leave the plug in and it's an unsteady flow problem where we have flow coming in but not flow coming out. So there are a lot of different scenarios. So defining the system, defining the time period, and the constraints or the characteristics of the system as we're analyzing it are important to recognize. Okay, so you need to know when you're supposed to start looking at the system. What is state 1? What's happening at state 1? What is my system? What are the inlets? What are the outlets? So it's going to start getting a little bit more complicated than it was when we analyze closed systems because we have additional factors that we need to consider. We need to look at now mass coming in and out and not just the energy interactions with the surroundings. For mass balance, the total mass within the control volume, we can just integrate this density times some differential volume across the control volume. And then we can find some rate of change of mass within the control volume by dividing through by dt. So this is, again, in the most general terms, showing things in terms of integrals and derivatives. But we usually make certain assumptions that allow us to find simplified versions of these equations so that we can analyze it a bit more readily. Okay, this slide looks a little bit scary. You won't ever have to do any of this. We're not in, what is the class? You have to do a lot of that. Mechanics of materials, something like that. But just jumping down to this bottom equation, basically what we're doing here is we're looking at mass flowing through a control surface, this differential amount of mass, and we're considering the different aspects of it, its speed and its its direction, and how much is going into the control volume. But at the end of the day, what we're really concerned about is these two separate integrals. The first is the rate of the change of mass in the control volume, and then the second is the net mass flow in and out. And you notice that's equal to 0. So in other words, we could move this net mass flow rate to the other side of the equation, and it would be the same as what we have looked at with energy, that the rate of change of mass in the control volume is equal to what's coming in and out of the control volume. And we make a lot of simplifications when we do this. So in general terms, we can rewrite that as a sum rather than an integral. And for steady flow, that means that there's no mass accumulation in the control volume. So this part of the equation, the rate of change of mass in the control volume, goes to 0. Okay, so all we have is mass flow rate coming in and mass flow rate going out. So if it's a steady flow problem, we can make that assumption. And if it's a single stream steady flow problem, meaning there's only one inlet and one outlet, then we can simplify it even further, that m dot 1 is equal to m dot 2, and we could break those down in terms of their density and velocity if we needed to. If it's steady incompressible flow, meaning that the density is not changing, we can also say that the volumetric flow rates in and out are equal. And then again, if it's steady incompressible flow, single stream, we can make that further simplification where we just have V1 and V2. When we were looking at closed system problems, we in many cases used the subscripts 1 and 2, and that indicated state 1 and state 2. So it was over some time period or interval that we analyzed the initial state and the final state. And we called them state 1 and 2, right? Okay, well now with steady flow and open systems, in many cases we're numbering the outlets and the inlets as 1, 2, 3, 4, 5. So be very, very conscious and careful with your subscripts and make sure you understand whatever you assign them to be, make sure you know what they relate to. So V1 and V.1 and V.2, it's not like an initial and a final flow rate. It's flow rate in and flow rate out because of the inlet and the outlet. Okay. So you can also use the subscripts I and O, but then you have to be careful you don't confuse it with initial and final. So for in and out, you just need to be very, very careful with your subscripts and make sure you understand, and it's clear to anyone who might look at your problem, what those subscripts refer to. So again, diagrams are very important. Draw a picture, label the inlets and outlets, and then make sure that you're keeping track. For one inlet, one outlet, it's pretty easy. When we start looking at problems that have multiple inlets and outlets, it gets very tricky and complicated quickly if you're not keeping track of your subscripts. Okay, so let's just do a pretty simple example. In this case, we have a nozzle with air entering steadily at 2.21 kilograms per meter cubed. And that number there, what does that represent? The 2.21 kilograms per meter cubed. What kind of a thing is that? What's that? Kilograms per meter cubed. Yep, that's the density. And what's 40 meters per second? Is a velocity. Okay, so looking at the units can help you determine what these terms are. If it's not said, the density is, you can know based on the units, and leaves at 0.762 kilograms per meter cubed and 180 meters per second. So we're given the initial and the final density and velocity in there. So if you weren't sure what those values meant, you would need to, again, go look at the units and make sure you remember and understand what those represent or what those symbolize. All right, so our unknown in this case, or what we're supposed to determine, is part A, the mass flow rate through the nozzle, and B, the exit area of the nozzle. So do we have any equations that we've learned thus far that can help us determine A and B? Okay, yeah, so m dot is equal to the density times the velocity times the area. Okay, and they ask us to find the mass flow rate through the nozzle. In this case, we're given the inlet and the outlet, but the mass flow rate in and the mass flow rate out should be the same. So 2.21 kilograms per meter cubed multiplied by 40 meters per second multiplied by 90 centimeters squared, and then we have to convert 1 meter squared is equal to 10,000 centimeters squared. Okay, so this gives us m dot 1, right? We're just looking at the inlet of the nozzle. So solving for m dot 1, we find it's 0.796 kilograms per second. So double checking my units, centimeters cancels out there. I have a meter squared and a meters, cancels out with meters cubed, so I'm left with kilograms per second. Perfect. Okay, so how do we find now the exit area of the nozzle? What do we know about this problem if we're assuming it's steady flow? Yeah, so mass flow in has to be equal to mass flow out. There's no accumulation of mass within the nozzle. So m dot 1 is equal to m dot 2, which means that rho 1, velocity 1, area 1 is equal to rho 2, velocity 2, area 2. We already solved this bit up here, this mass flow rate 1. We're trying to solve for area 2. So area 2 is equal to m dot 1 divided by the density of the outlet multiplied by the velocity of the outlet. So m dot 1 over rho v2. And if we plug in the numbers for that, we get 0.796 kilograms per second divided by 0.762 kilograms per meter cubed and 180 meters per second is 0.058 meters squared, which we then can convert back into centimeters, so 10,000 centimeters squared per meters squared gives us 58 square centimeters. Okay, so it's a relatively simple problem, nozzles are, but it's a good practice to go through something like this to see how the units work out and also to remember the relationship between density, velocity, area, mass flow rate, and then knowing that it's steady flow allows us to equate the mass flow rates one to another. So we have mass balance. Flow work is the work that's required to push mass in or out of a control volume. So if we're moving a fluid through some distance L, the flow work is equal to the force times the distance, or F times L. I think this laser pointer works now. Yeah. And this force, for fluids, it's quite often a good, well, the force is often due to the pressure of the fluid. So this force can be rewritten as pressure times area times L, whatever the distance is that we're moving it through. And we can combine these two terms, A and L, so the area times the distance will be equal to the volume. So the flow work is just the pressure times the volume. And per unit mass, it will be the pressure times the specific volume. So sometimes we look at flow work as actually an energy term rather than a work term because it's a combination of two property values. So sometimes rather than looking at it as a work, like a force through a distance, we think, well, it's actually more like energy because it's inherent to the fluid itself that it's this pressure times volume. So previously when we talked about the difference between heat and work and energy, energy can be possessed by a system, but work and heat are not like defined properties of a system, whereas flow energy, we kind of can define it as a property of this system because it's a combination of property values. So regardless, the units on it are units of energy, so whether we look at it as a work or an energy term, it really doesn't matter as long as we analyze it correctly. So for a simple compressible system, that would just be the closed systems that we've been analyzing up to this point, we found that the energy is just equal to the sum of the internal energy and kinetic energy and the potential energy. So that's the energy in a system. But for a flowing fluid now we have this additional flow work term. So instead of saying E, we use this theta to represent the energy of a flowing fluid. So it's equal to these same terms as before, the internal energy plus the kinetic energy plus the potential energy, but now we're adding in this flow work term, or this PV. And this PV, what does that look like that we've seen previously in closed systems? Maybe like a piston cylinder device. Pressure times volume, or pressure times the change in volume. What was that? Do you remember? Say that louder. Where have we seen something before where we're looking at an energy term that's pressure times volume in a closed system? Ideal gas law, we do see that, but that's not really energy terms. That's just a correlation of properties. I'm talking about boundary work, right? So it's similar to boundary work, but it's now, instead of at the boundaries, it's like inside the system, because this fluid is moving through the system. Just like on our closed systems, when our boundaries started moving, we had an additional work term. Okay, that's analogous to this. And similar to what we did previously when we had problems with boundary work, we combine those two terms, that U plus PV, into one term, H. Okay, so now when we do our energy balance and we write our big energy equation for an open system, Q in minus Q out plus work in minus work out. This is for a closed system is equal to this, usually just the mass times U2 minus U1. If we're neglecting kinetic and potential energy, which we almost always do. However, for an open system now, in many cases, we're looking at it in the rate form. So we have a Q dot in minus a Q dot out plus a work dot in minus a work dot out is equal to M dot times H2 minus H1. So that's the major difference in the energy equation for a closed and an open system. Coming up on the next exam, you will probably have problems that may be a closed system or maybe an open system. So one of the first steps when you're defining your system is to determine, okay, is this a closed system or an open system? And if it's a closed system, which correlation do I use? If it's an open system, which correlation do I use? Okay. And understanding fundamentally the difference in those two and why that comes about. So that why is there an enthalpy term in an open system? Well, it's because of this flow work. Okay, so we just derived that here. We just showed that it takes into account the idea that this fluid now has energy associated with the movement of it. Okay, just like boundary work, but now it's like within the walls or inside the system itself. So this energy can be transported by mass. So this change in energy of the system, or this E of the mass, is equal to this M times theta, or we can look at it in terms of changing per time, which would be an E dot. And then the general correlation equations, which are in the integral form, which we don't get into a lot in this class, but there they are for your reference, and those are in your book as well. So let's look at another example. So in this case, we have a duct, and we're going to have some air flowing through it. Okay, so this is a simplified version of a problem that comes later where we actually start looking at the work interactions. But in this case, a hairdryer is basically a duct of constant diameter in which a few layers of electric resistors are placed. A small fan pulls the air in and forces it through the resistors where it is heated. If the density of air is 1.2 kilograms per meters cubed at the inlet and 0.95 kilograms per meter cubed at the outlet or exit. Determine the percent increase in the velocity of the air as it flows through the dryer. So we know the density in and the density out. We need to find the percent increase in velocity. So how would we approach this problem? Thinking of it in terms of mass conservation, what do we know about it? Yeah. So is there like air that's getting trapped in the hairdryer and it's not moving? No, it's everything that's coming in is going out. So the mass flow rate in is equal to the mass flow rate out. So m dot 1 equals m dot 2. Okay. How does mass flow rate relate to density and velocity and area? Yeah. So density times velocity times area. So the density coming in multiplied by the velocity of the air coming in multiplied by that cross-sectional area that the air flows into is equal to the density going out multiplied by the velocity going out multiplied by, again, that cross-sectional area. What is the same in this problem? Is the density the same? Is the velocity the same? It's increasing, right? We're supposed to find the percent increase. So the density changes. We're given those values. The velocity changes. Does the area change? No. We can assume that the cross-sectional area is the same. So that can cancel out of the equation. We're simply left with density times velocity of the inlet is equal to the density times the velocity of the outlet. And if we want to know this percent increase of velocity, that's just V2 over V1 is equal to density 1 over density 2. So if we plug the numbers in for that, 1.2 kilograms per meter cubed divided by 0.95 kilograms per meter cubed. So we find that it's a 1.263 ratio. What would be the percent increase? So in other words, V2 is 1.263 times V1. What if V2 was equal to V1? Would there be any increase? No. What if V2 was twice V1? Would there be any increase? What's the percent increase? Okay, it's not 126%, it's 26.3% increase. Okay, so if it's double, that's a 100% increase. Yes, yeah, it's a 26.3% increase. Okay, so that terminology, sometimes understanding what it means physically and how you find it are two different things. Okay, let's do another example. This used to be, actually it is still problem 511 in your book. This is not a homework problem that you're doing.
A spherical hot air balloon is initially filled with air at 120 kilopascals and 35 degrees Celsius with an initial diameter of 3 meters. Air enters the balloon at 120 kilopascals and 35 degrees Celsius with a velocity of 2 meters per second through a 1 meter diameter opening. How many minutes will it take to inflate this balloon to a 15-meter diameter when the pressure and temperature of the air in the balloon remain the same as the air entering the balloon? So we know the initial pressure and temperature. We know that the pressure remains the same, and we're given the initial and final diameter as well as the diameter of the opening of the balloon.
Okay, so there's a lot going on in this problem. Sometimes when it's a complicated problem like that and it has all these different dimensions and diameters and sizes and everything else, it's best to take a step back and do what? What's that? Okay, we can write the equation, but even before we write the equation, what should we do? Draw it, right? Okay, so this balloon starts out, we're approximating it as spherical with a little hole in the bottom. Second. Okay, right? So we took all those numbers that were given to us in that problem and we put them in a more readily accessible form in that picture. Okay. So, still, how do we solve it? What do we know about this problem? There's some assumptions that I've already written down. So air is an ideal gas. That's good for us. It's not water. If it were a water balloon, it'd be more complicated. We can assume the density is not changing because the air temperature and pressure have not changed. And we can assume that the flow into the balloon is steady. So if we're thinking about this problem in terms of mass conservation, what would we expect would be the result from state 1 to state 2, or from an initial state to a final state? Would there be mass accumulation, a mass decrease, the same amount of mass in the balloon, right? Okay, so from mass conservation standpoint, it is conserved, but it's not balanced initial and final, right? So there's going to be some change or accumulation of mass within the system. Okay, we're often it's usual that we want to know like the volume of a system. So how do we calculate the volume of a sphere? Does anybody know that equation? Yeah. So an area of a circle is pi d squared over 4, right? Yes, pi d squared over 4. So if we were to derive that, okay. So area or volume of a sphere is equal to pi d cubed over 6. Right. Hopefully that diameter opening is the same. Yeah, okay. Pi d cubed over 6, if we put in the numbers pi times 3 cubed over 6, that's meters, we get an initial volume of 14.14 meters cubed. Our final volume, or V2, is pi times 15 cubed over 6. That gives us 1767.15 meters cubed. Okay, so we know initial and final volume. What else do we know about this system? Or what can we calculate? What might we want to know? Density. Okay, so we could calculate the density or the specific volume, because that's what comes up more often. So specific volume is RT over P for an ideal gas, 0.2870 kilopascals times meters cubed per kilogram Kelvin is R. The temperature, we have to use Kelvin, right? So 35 Celsius is 308 Kelvin. And then our pressure is 120 kilopascals. So we find our specific volume is equal to 0.7366 meters cubed per kilogram. Okay, so we know volume, we know density. What else might we want to know? We know the velocity of the air coming in. Do we want to know the mass flow rate? Probably, right? So mass flow rate is equal to the velocity times the cross-sectional area times the density, or divided by the specific volume. So that's what we solve for here, the specific volume. So our cross-sectional area is this 1 meter diameter opening. So we have 2 meters per second multiplied by this pi d squared over 4, so 1 meter squared over 4, and then divided by our specific volume, which is 0.7366 meters cubed per kilogram. So our mass flow rate we find is 2.132 kilograms per second. Okay, I feel like we're getting closer to figuring out how to solve this problem. We ultimately want to know how long it takes to fill the balloon. So we know how much mass can go in with time. What is the other piece of the puzzle that we don't have yet? Yeah, the initial and the final mass. So we can calculate that. We know the volume, and we know that mass is equal to total volume divided by specific volume. So the mass initially is this pi d cubed over, well, actually this is, the volume is pi d cubed over 6, and then we divide by this specific volume that we determined from earlier is 7.366 meters cubed per kilogram. So we can put in the diameter of the initial state to find the mass of the initial state, and the diameter of the final state to find the mass of the final state. So the initial mass is times 3 meters cubed divided by 6 times this 0.7366 meters cubed per kilogram. And that's 15.19 kilograms of air. And then our final mass, M2, is equal to pi times 15 meters cubed divided by 6 times the specific volume, 7.366 meters cubed per kilogram. So we get 2.399 kilograms. So M2 minus M1 will give us our change in mass, which is equal to this 2.399 minus 19.19. Kilograms, which is equal to some 2.3, we'll just say 80 kilograms. It's actually going to be 79.81. Is that right? I'm doing math on the fly. Tell me if that's right. Okay. I did math. Sometimes my brain quits working when I stand up here. Okay, so now we know the change in mass. We're still looking for the time interval. How does that relate to the mass flow rate? We want to find seconds or minutes. We've got kilograms. We've got kilograms per second. Divide it. Okay. So this delta M over some time interval is going to be equal to our mass flow rate, right? Right? So delta M over delta T is equal to M dot, kilograms per second. So we can find delta T is equal to our delta M divided by the mass flow rate. And we calculated our mass flow rate to be 2.132 kilograms per second. Our change in mass is 2379.81 kilograms. So if we plug in the numbers for that, delta T is 1116.2 seconds, or that's 18.6 minutes. Okay, so this would be an example of an unsteady problem where we're filling up some volume at 35 degrees Celsius. and we're trying to figure out how long that will take, how much mass accumulation will occur over that time interval. So we apply conservation of mass to the problem, that the mass in, or the mass out minus the mass in is going to be equal to this delta mass to figure out how long that will take. Okay, so this one, this compressor example is a little bit more similar to your homework problem than this hot air balloon problem. So let's take a look at that. Because as we move through Chapter 5 and into Chapter 6, we start seeing a lot of nozzles and compressors and turbines and pipes and all of these steady flow devices that we will have to learn how to analyze. So it's important to know that. Okay. So we have an air compressor that compresses 10 liters of air at 120 kilopascals and 20 degrees Celsius to 1,000 kilopascals and 300 degrees Celsius. Determine the flow work in kilojoules per kilogram required by the compressor. Okay, so the question is asking if we want to take air, a certain volume of air, and increase the pressure, which by doing so will increase the temperature, how much energy is required to do that? So we don't know the flow work, but we do know initial and final states, and we know the total volume of air that we are going to compress. So we can make the same assumption that air is an ideal gas, and that our compression process is a steady process, meaning we're not like oscillating and compressing it in a non-steady fashion. So flow work, as we derived it in the lecture thus far, is what? What is flow work? So we're trying to find the flow work in kilojoules per kilogram. What is it? Yeah, it's pressure times volume. So it's like the energy required to change the shape or move the fluid through the system. So this flow work, and when we look at it in terms of kilojoules per kilogram, it's a lowercase w. The flow work is equal to pressure times specific volume. And in this case, because we're assuming that it's happening steadily, we can say that P2 V2 minus P1 V1 is equal to the flow work. Okay, we know the initial pressure, right? Do we know the initial specific volume? Okay, we know the total volume, right? So we could calculate it using the mass. Do we know the mass? No, we don't know the mass. But what do we know? It's an ideal gas, right? We know how to relate pressure and specific volume and temperature and other things together. So we can use the ideal gas equation, and we can solve explicitly for the specific volume at state 1 and state 2, or if we remember that PV is equal to RT, we know R, we can look that up, and then the temperature is given. So we can rewrite this as RT2 minus RT1. Okay, your problem in your homework is not an ideal gas. I think it's R134A. You cannot do this. You have to actually go to the property tables and look up the values. Yeah, yeah. But it would be PV equals MRT. And you would know V, yeah, so then you could find it. But. Okay, so RT2, so 0.2870 kilopascals times meters cubed, or kilojoules per kilogram. It's the same thing, kilojoules per kilogram Kelvin. In this case, I'm multiplying by temperature, so I don't want kilopascal in there. And then just the change in temperature. And I can convert both of these to Kelvin and plug it in, or I can leave it as Celsius because it's a delta T. Okay, so if I put in 300 Celsius and 200 Celsius, That's going to be the same as if I converted both of those to Kelvin, because the offset cancels out anyway. So our flow work is equal to 80.36 kilojoules per kilogram. Okay, so the difference in the problem you have to do for homework, and that problem is 21. So you're given some information about it. Refrigerant 134A enters the compressor of a refrigeration system as a saturated vapor at 0.14 megapascals. So what's your state 1 in the homework problem? So at 0.14 megapascals saturated vapor, are you given enough information to fix the state? Nobody knows. Let's look at the dome. Where is saturated vapor? Right here? On that side, right? And you know the pressure. So can you look up property values right there? What are they in the tables? Yeah, saturated vapor problems or properties. So things with a subscript G. So V sub G, U sub G, H sub G, right? So you can fix the initial state, and then it leaves as a superheated vapor at 0.8 megapascals and 60 degrees Celsius, okay? So superheated vapor, and you're given the pressure and temperature. Can you fix the state? Yeah. Okay, so instead of plugging in this R2T2 minus R2T1 into the problem using the ideal gas equation, you have to actually find the pressure and specific volume at each of those states. Okay, it's not any more difficult to do, really, if you know what you're looking for. So again, remember, you can fix the state as a saturated vapor using the saturated vapor properties, or the V sub G property. And then for superheated vapor, you're giving the temperature and pressure, so it should be easy to fix the state also. Okay, any questions? All right, I'll see you next Tuesday. Homework is due. If you have questions, send me an email. Get started on it so that you're not waiting till the last minute, and I will see you next week.